Hi, I'm Andrew Portolese, and I'm presenting a paper entitled Distributed Representations of Sentences and Documents, which is from 2014 by Kwok Lee and Thomas Mikolov. The problem this paper is attempting to solve is both text classification and sentiment analysis. Existing methods will often lose the order of words, which, as we know from speaking, is very important to the meaning or the sentiment of the paragraph. And these methods often ignore the semantics of the words instead of just capturing the frequency. Some existing solutions include bag of words, bag of n-grams, and recursive neural networks. Another issue is that inputs to these existing models require a fixed length vector, preventing us from inputting a variable length paragraph. Bag of words is a feature extraction method using machine learning that takes a selected vocabulary of words and extracts the frequency of those words as a result. The problem with this approach is that the word order is lost, and it doesn't capture the meaning of these words or the relationship to other words in the sequence. The approach in this paper is described as a paragraph vector. It is an unsupervised algorithm that uses stochastic gradient descent and backpropagation. It learns fixed length features from variable length paragraphs or documents, and the algorithm has two parts. First, it trains a neural language model to get word vectors and known paragraph vectors. Then the inference stage trains to get new paragraph vectors which are used in the prediction of words in the paragraph. To generate the word vectors, a neural language model is used. Each word is represented as a one-hot vector shown in the diagram as matrix W. Then a sequence of words is chosen and their vectors are added together to create the input for the neural network. The paragraph vectors are created in a similar way, but a sliding window over the words in the paragraph is used. The neural language model used consists of a reward function that maximizes the average log probability, shown as the first image, and it uses a hierarchical softmax activation function, shown as the second image. The paper describes using a binary Huffman tree because it provides performance improvements over a normal softmax by speeding up the lookup of commonly used words. This neural language model produces a model where words with similar meaning are mapped to a similar position in the vector space. For the paragraph vectors, an algorithm called the distributed memory model of paragraph vectors is used. Each paragraph gets mapped to a unique vector similar to the way word vectors are created. A sequence of words is concatenated with a paragraph vector to create the input for training. The paragraph vector is created by using a sliding window selection over the words in the paragraph. At inference or prediction time, new paragraph vectors are trained to create the input for a prediction, and the paper notes that it took 30 minutes to produce this paragraph vector with a now modest computer. This is probably the biggest negative of this method since it requires training for new or unknown paragraphs. There are many benefits to this algorithm. First, it's unsupervised, so it doesn't require any labeled training data. The word vectors generated provide the semantic or contextual meaning of the word. One of the examples often used in the paper is that semantically the word powerful should be closer to the word strong than the word Paris, since powerful and strong are similar adjectives, while Paris is a place. Another benefit is that the paragraph vector takes into consideration the context of a paragraph. One of the existing methods, bag of n-gram words model, does capture the word order, but it does so in a way that is very specific to the training data and doesn't generalize well. The paragraph context captured in the paragraph vector generalizes better, even though it doesn't capture the exact word order. Another algorithm that is used is called the distributed bag of words version of paragraph vector. It takes the generated paragraph vector in as input and predicts words from it. For this model, during the training of stochastic gradient descent, the sample word sequence window and a random word from the text window are used to form a classification task given the paragraph vector. One benefit of this method is that it uses less memory since it only stores the softmax weights. For the experiments in this paper, they found that a paragraph vector generated by a combination of the distributed memory model of paragraph vectors and the distributed bag of words version of paragraph vector worked best, and this is what is used for the following three test datasets. The first is sentiment analysis with the Stanford Sentiment Tree Bank dataset, which is 11,855 sentences of reviews from Rotten Tomatoes with scores from 0 to 1. The second is sentiment analysis with an IMDb dataset, which contains 100,000 movie reviews, and it was mentioned that these movie reviews are not just sentences, but they are also paragraphs. The third is an information retrieval evaluation, where the dataset contains the first 10 results from a search engine for the top 1 million search queries. The results for the sentiment analysis test show that this algorithm performed the best out of all existing methods. They compared against naive Bayes, SVMs, word vector averaging, and recursive neural networks, most of which are what this paper and algorithm are based on. For the Stanford dataset, the two scores represent two scales for the sentiment, and the paragraph vector did best on both. For the IMDb dataset, results are also really good. One thing to remember is that the paragraph vector model requires training while doing the inference and takes much longer than many of these other methods. For the information retrieval test, a success is considered when the distance of the results generated by the model is within a certain threshold, where the distance of the first two paragraph vectors is closer than the distance of the first and third paragraph vectors. Again, as you can see, the paragraph vector method did the best of the other methods tested. Thank you.